Suresh sir for giving me this opportunity to talk. So today we will talk briefly about Superblock scheduler for code-sensitive applications. So this is a joint work with Chris Wick and Sudarshan Veeravalli, my colleagues at Qualcomm. So yeah, so this is going to be the structure of our talk. So first we'll go through motivation and then have a overview of superblock scheduling, and then we will see what are the constraints that embedded applications pose, and we will see how these constraints are overcome in our implementation, and we'll have an outline of our implementation in LLVM. Then we'll see how our scheduler, we'll have a glimpse of the performance of the scheduler, then look at the limitations and see what we can do in future. So, so one of the load latency and branch penalty limit performance in order CPUs that every one of you may already be aware of it. So if we have small basic blocks, then that means that we may have to take branch penalty often, and the scheduler also, instruction scheduler may also not be able to hide load latency. Just one thing, if something is not clear, then please interrupt me right away. Okay, so this everyone knows that. So for instance, we have a code like this where we load from an address into the register R0, and then we branch on depending on whether R0 is 0 or not. If R0 is not equal to 0, then we take a branch, or if it's not, if it is equal to 0, then we go through fall through computation, um, where we have some unrelated computation, and then we take another branch. So we can see that there is a load, and immediately followed by this load there is a use of this value loaded. So if we have, say, a load latency of some 2, 3, 4 cycles, 5 cycles, then in order, if we have an in order CPU, then it will be then there'll be stalls. And so this is a and this kind of code is not uncommon. um, so 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 this is one of the main motivation to go beyond a basic block scheduler. So so what do we do in super block scheduling? So first, what we do is, suppose we will we will build control flow graph with annotated with branch taken frequencies. For instance, if you take this if you take this part of a control flow graph, we can see, can you see which path it gets taken more often? Can any one of you tell me which path is very taken very likely? Suppose we start from BB0, where are we likely to go in most cases, more than 90% of cases? BB1 or BB3?
So in the chat box,
Arun, there are answers on
messages.
chat. Yeah.
Oh, okay, okay.
I'll speak. I'll speak, Arun. You keep on the presentation. You go on the
Okay.
presentation. So one web house says BB0, BB3, BB4. Prajwal says BB4. Yeah.
Right. Yes. Thank you very much, Sushim sir. Yes, you're right. So we will be most often taking the path BB0, BB3, BB4. That is the sequence that we will be taking most often. From BB0, we are more likely to go to BB3 than BB1. So this sequence of basic blocks is called as a trace, where more frequently executed path, it's called a trace. Okay, so what we do in What we will do in superblock scheduling is first we will identify traces, and then we will place the basic blocks in the trace sequentially. Why is that? Why is it preferable to do that? For instance, if in the final code layout, if bb1 is placed, uh, which one is which basic block do you think should go right behind bb0? That is, which one should be at the fall through of bb0? Should it be bb1 or bb3? Assume that we have a taken branch penalty of 5 cycles. Which basic block should be the fall through of bb0?
Arun, we have an answer BB3 coming from Prajwal Krishna.
Yes. Why? Thank you, sir. Why is that? What if we place bb1 immediately behind bb0? What if bb1 was the fall through of bb0?
So we keep paying penalty almost all the time.
Right, exactly. So that's a very good answer. Yes. So we want to place the place the bb basic blocks in the trace sequentially. So that is one of the that's how we deal with taken branch penalties, avoiding taken branch penalties. It's okay if sometimes we go off trace, that is if we go to bb1, sometimes if we go, that's fine, as long as we are following this sequence of basic blocks. Most of the time we will be able to get the benefit most of the time. So yes, so we place the basic blocks in the trace sequentially, and then we schedule the instructions treating the sequence as a single basic block. So um, this is how we can describe superblock scheduling in a nutshell. So let's go through what I mean. If we do this, then there are going to be some complications, because we may move instructions across branches. So how do we deal with them? Let's look at how we can deal with it. Okay, so okay, just focus on the left hand side graph, I mean left hand side pair. So in this sequence, in this control flow graph, um, assume that the trace is I1, I2, I3, I4, I5. Okay, so here I3 is called, this is not the complete control flow graph, so forgive me for I mean hiding the uninteresting details. But what we can see is that uh, from I3, and we can have a off trace, I mean I3 is called a side entry of this trace, because we have a control flow coming into I3 from non-trace path, that is from I6, which is not inside the trace. So this is called an side entry. I3 is called side entry. So assume that we want to move I1 after I4 in the schedule. So what will be the, I mean, what will be the consequence of that?
So
So
quick question, are the I1, I2, these are instructions or basic blocks?
yes, we can. Okay, so we can consider them to be basic blocks, and suppose we, yes sir, so we can treat them as basic blocks. Okay, so suppose we want to move an instruction in from I1 after I4. So what will happen if we do that? Or you can consider them to be just instructions, single basic block, I mean single instruction basic blocks. For simplicity's sake, let's take that they are all single instruction basic blocks.
Arun, there is a question in the box. You take them at the right, take it at the right time, but let you know. How
Okay,
are
okay.
these percentages being calculated? Won't they require code execution?
Yes, yes, sir. That's a very good question. So
Hmm.
this requires profiling, what is called as profiling, where we um, where we run the code with what is called as train inputs. Okay, so uh, okay, this one we may one valid question is what if one valid concern is will this train input be representative of the program execution for all inputs? If the train inputs do not characterize if the train inputs do not characterize the program execution in most cases for most inputs, then it's not going to work. But there are several important classes of applications for which we can characterize the program behavior with a very small set of inputs. So we are focusing on those kinds of applications only. So does this answer your question?
Yes, I think so. Yeah.
Okay. So yeah, so we are the assumption is that we have this frequency. So okay. So now coming back, wow. So when will this? If suppose if we want to move I1 after I4, so okay, in the if we are following the trace, then that's fine because it's okay. But what if we take what if we enter I3 through I6? What will happen if we do that? So we will be executing I1 unnecessarily, right? Is it clear?
But not really. Are we talking about the left side picture or the right side picture?
Left side picture. I mean, so we have two pairs of boxes. We are
Yeah.
talking about the left side pair, and particularly from to the left side box. Before we are considering the original trace. Suppose if we move I1 after I4, then
Arun, there
suppose
is a
that
question in the chat block. What does moving I1 after I4 mean? Is the source code being changed, or are we doing some optimization step?
yes, sir. Yes, the source code is being changed. I mean, we are transforming the program. We are
Okay. Okay.
so
So, but the semantics of the program will change here, right? If you don't respect the dependencies, Arun.
yeah, yes, sir. So, assuming that I1 and it is legal to change it is legal to move I1 after I4. There is no data dependency.
Oh, okay. So assuming, so then in which case the point you're making is in the second line of execution, unnecessarily we'll end up executing I1. That's
Yes, sir. Yes.
okay. Got it. Yeah.
So yeah, so one thing is that some okay that may be so if we are paying that penalty of executing I1 infrequently, that's fine. But what if I1, suppose if I1 can raise an exception, then is it okay to move I1 after I4? Suppose that I1 is a load or a floating point instruction which can potentially raise an exception. So is it legal to move I1 after I4?
Yeah, good point. I didn't see that. Yeah. Yeah. So
Yeah, so we may not so we should so if I1 can raise an exception, and then if we move I1 after I4, and then we take a off trace path, that is we don't follow this trace, but we enter I3 through I6, then what will happen? We execute I6, then I3, then I4, then I1, and then take an exception. So, but if the in the original program, however, the exception wouldn't have been taken. So this is not correct, right? So what we have to do is whenever we move code below a side entry, we have to make some we have to be more careful. For instance, you take this right hand. I mean, can you see how I'm moving the mouse?
Yes, sir. We are able.
Yes, thanks, sir. So but you take this code. I mean, consider this case where we have transformed the code like this. After I6, we are placing a copy of I3 and I4, and then we are going to I5. Here I2, I3, I4, I1, I5. So in this case, will I1 be executed if we follow an off trace path?
No.
No, right? So this is the change that we have to make when we are moving code below a side entry. Similarly, if we want to move some code above a side entry, for instance, if we want to move I5 before I2, then what we have to do? Then we have to place a copy of I5 when we take the off trace path, right? Otherwise, we wouldn't be executing I5 at all in the off trace path. So this is how we have to do. Is the right hand side transformation clear? Or is there any doubt in the why we have to transform code like this?
Yeah, I think the transformation is clear, assuming the dependencies are preserved. But what is the specific advantage we get? Because
Yes, sir. So, what is the specific advantage of doing this?
this
Yes, sir. So we are able to move instructions. I mean, for instance, if there is if I1 is a long latency operation, and we want to hide the latency of I1 before it gets used at I2.
so you want to increase the trace length. That's what we are trying to do. Okay.
Yes, sir. By increasing, I mean, if by having this 5 basic block trace, we are able to hide the latency of I1. So that's the advantage. If we move I5 between I1 and I2, then we are able to hide the latency of I1 and reduce the number of stalls.
Yeah, so the reason I asked that question is so the frequency of 14 I4 and I5, they are the same. So instead of moving both I4 and I5 there, why are we moving only I5? Is there any design decision behind that?
Oh, okay,
That's
sir.
the question. That's the motivation behind the question.
Okay. So there is no such, I mean, this is just for an example. Assuming that only this moving I5 to I1 is after I1 is legal. We cannot move I4 after I1 due to some data dependence or something. Just let's assume like that.
Okay.
Data dependence prevents moving I4 after I1. So this is just an example to illustrate what are the things that we have to do when we move code above or below a side entry. This is just for illustration.
Basically, Arun is building a case for like super block scheduling we chose to present today because in our something we did internally, it showed a drastic performance improvement So that is the reason that we are talking it about today. Like it showed such a drastic improvement that it made end customer impact in things. So he's just building the case right now.
Yeah. So there is one question from student from Sanjana. So what exactly is meant by hiding latency by moving code like this and replicating code? So the possible reason for this question is I didn't talk about instruction scheduling so much in the class. I just mentioned it briefly.
Okay, okay, sir. So, so maybe I'll take an example. Can uh, how I can is it possible for us uh, to see, are you seeing me now?
Not, no, we are not seeing you.
Okay, is it possible to uh, switch on my camera?
Yeah, of course you can. Yeah.
Okay, sir.
You just have to enable video from your side. I think
Okay,
it
sir.
is.
Okay, sir. Just give me a moment. Mm, yeah. Mm,
So, Arun, while you're doing that, probably you can answer the other question also when after you
yeah.
finish this video. Like there was the other question, like how do we know if that there is no dependency? I think this is dependency
Uh,
across basic.
Ravi, that is cleared by Arun. He said he answered that question. Ravi, you need to go to yeah, and you need to unshare it. Arun, we are able to see you, but you need to unshare it. Unshare.
oh, okay, okay.
Stop sharing. Then you will be the big on the screen.
Okay, Sushim. Okay. Yeah. So yes, just to thanks, Ravi. Yes, just to reiterate, we will know the dependencies, data dependencies when we construct the dependency graph. Okay. So can you see the board?
No, you're
No.
seeing slides.
Oh, okay. Oh, but we cannot see the board.
See, it is
Actually,
possible. Maybe I can quickly clarify to the students. It's like this. Like so, let's say if there is a load instruction, load R1 followed by some address, and then followed by that there is another instruction. Like for example, add R3 comma R1 comma R2. So there is a dependency from load instruction to the add instruction. So and that induces latency. But if we can move an instruction in between, for source operand doesn't depend on the load operand, then that instruction can launch and it can start executing. So like this, we try to move instructions around so that so that we increase the gap between two dependent instructions, so that by the time the dependent instruction is launched, all the required source operands are already available, and it can go ahead and execute. But if the basic block size is very small, it is difficult to, we don't have enough instructions to move around so that we can hide these latencies. So the whole exercise that we are trying to do here is we are trying to increase the trace length, the basic block length, and so that we get more opportunities for moving instructions around and thereby hide the latency. And if you see the slide that you are seeing on the screen, on the left-hand side, there's a pair of rectangles. So by moving from one side to the next side, we are able to like for example, by moving in this particular example, we moved I4 to up the chain. By moving that, what happens is the trace length has increased, and thereby we got more opportunities for optimization. And we cannot simply do that because because there are other paths, other execution paths that we have to take care of, and that's what is being done. So the goal is how we can increase the trace length or basic block lengths so that we can get better instruction schedules without violating the program properties, that is legality. And the first example on the left given by Arun is very nice, because during this process, we don't want to induce unexpected no faults in the program. So that's a quick summary of for what what we are attempting to do here. Is that a right description to say, Arun? I mean, or would you like
Yes,
to
sir.
add?
That's a very nice way of putting. Thank you very much, sir.
So I think we can. So you can still go ahead and share your whiteboard and whatever you want to do, Arun. But otherwise, we can move on. Also, you can decide what.
Yeah. I think sir has summarized it very nicely. So that's what I want. I also wanted to do. So
Sure.
so we'll go ahead.
Yeah,
So
we should move ahead in the interest of time, Arun. Yeah.
yes, Sushi. Yes. So that. So I just wanted to, put these slides in order to see that, in order to show that it's not, we just cannot simply move instructions up and down. We have to, for instance, in this slide, we can see that we are inserting copies of instructions, right, into the program. Okay. So now this is regarding moving instructions up and down, below and above a side entry. Let's talk about side exit. Dealing with side exits is relatively simpler. Can you see the slides?
We are seeing, but we didn't move to the next slide.
Yeah.
So
Okay. Probably I think I should turn off the video.
yes.
And you move to the Arun. You go to the slideshow and change it. Yeah, please.
Okay, Sushi. Can you see now? Can you see the? Oh, okay. I have to share, right? Resume.
It's already on sharing, Arun. Yeah.
Yeah.
Side
Okay.
exits. Yeah.
Are we
We are able to see
seeing?
it. Yeah, we are able to see the side exits. Yeah.
Okay, we are seeing a different slide, right?
Yes.
Movement across side exits. This
Yes.
is relatively simpler. So, consider this trace B1, B2, B3, and B2 is a side exit of the trace. That means that we are having there is a non-trace successor of B2, that is B4. Suppose that um, we want to move um, move b x equal to y plus z below b2, for instance b3. Can we do that? What if we move this instruction x equal to y plus z from b1 to b3? Can we do that?
So we get into trouble in B4.
Yes, sir. So the definition x equal to y plus z will reach B4 in the original program. Will reach the use of x in B4 in the original program, right? But if we move this definition below B2, then probably x may be undefined, or it will have an older definition of x, which is not correct. So what we have to do is we have to place a copy of this definition at the side entry also, right? We have to do it only when x was live in at the side exit, at B4. Suppose if x was not at all live at the beginning of B4, then we can surely move this, right? Why is that? When x is not live in at B4, is it okay to move this to here, to B3?
Yeah, I guess so. But
Yes,
the
sir.
equal to x should not be there, no? Or is it?
Yes, sir. That if x was assuming that if x was not live in at B4, then we wouldn't have this equal to x.
Yeah, sure.
Or there is
at the beginning of B4.
Yes, sir. So or there is a definition of redefinition of x without using it.
Okay.
In that case also we can move this. So suppose if we want to move moving if suppose we want to move an instruction above a side exit, then what we should do, then these are the precautions that we have to take. We cannot move a definition above a side exit if the defined value was live in at B4. So similar, the same case. Or another thing is that we should not move an instruction above a side exit if that instruction may raise a fatal exception, right? When the side exit is not taken. Okay. So why is, suppose that we have a floating point instruction that divides by 0 at B3. Okay. Can we move it that divide by 0 to B2? Let's consider two cases. When the trace, when we are following the trace, that is when B1, B2, B3 gets executed, it's okay to take, it's okay to move this instruction to B2, because anyway we will be hitting that exception at B3, so it's okay. But what if B3 was never executed? What if B1, B2, B4 was always executed? In that case, we would have executed this divide by 0 instruction at B2, so which is a violation of program semantics, right? So is it clear?
Yes, very much, sir. It's very clear.
Okay, sir.
Yes.
So this is
Arun, you might have to, Arun, you might have to expedite. We have 20 minutes remaining.
Yes, Sushin sir. Yeah. So just that the point that I wanted to make is that moving across side entries is difficult. Moving across side exits is relatively easier, because if you can see, if we have to move above or below a side entry, then we have to insert some instructions. On the other hand, when we can move an instruction above a side exit without any overhead, if we can show that the moved definition was not live at the entry of the side exit. So that this is all I wanted to make by these examples. Okay, so okay, so now we have an idea of what exactly we need to do when we move instructions above or below a side entry and side exit. So we saw that side exits are more easily managed than side entries. So what we do is we have to transform the code such that there is no side entry. So how do we do that? By code duplication. For instance, you take this trace BB0, BB3, BB4. Can you tell me at least one side entry in this trace? What is a? Can you name one side entry in this? Oh, in this trace?
From BB1 there is, yeah, BB1 to BB3. Once to Vaibhav's answer.
Yeah, yes, sir. Yes, Vaibhav. So BB3 is a side entry here, because we can enter BB3 from an off trace basic block BB1 or an off trace basic block BB2. So BB3 is a side entry. So we have to get rid of side entries. How do we do that? We just duplicate code from BB3 to BB4. So from BB3, from a side entry, you duplicate the trace. Okay, the remaining part of the trace is BB3 and BB4. Whatever incoming edge was there into the side entry, you direct those edges into the copies of the replicated blocks. That is, initially BB3 had two incoming edges, right, from BB1 and BB2. Now those incoming edges I mean, those outgoing edges from BB1 and BB2 are directed to the copy of BB3 that we have replicated. And similar, so this is how we convert. So this is how we get rid of side entries. So this is actually a super block, a trace without a side entry. This is actually a super block. So because moving across side entries is very complex and is often error prone, we simplify the traces to form super blocks where there is no side entry. So we achieve this by duplicating what is called as tail. A tail is a part of the trace that starts from a side, from the first side entry, and ends at the end of the trace. In this case, the tail is BB3 and BB4. So we replicate BB3 and BB4. So this is how we convert a trace with side entries into a super block without any side entry. There may be side exits, but they are easy to manage. Okay, so
one
what
question, Arun, here, quick question.
Yes, sir.
So not exactly related to this algorithm, but in superscalar processors where branch prediction and you do aggressive out of order execution,
Yes, sir.
does this super block approach help, or is it only the case with in order processors where we have
Yeah.
the compiler has to work hard to provide opportunities for the processor to execute things in parallel? So,
Yes.
what is any
So,
insights on this? I mean, how impactful is this in superscalar processors?
Yes, sir. So so in super this will be more impactful in order processors. So for an out of order superscalar processor, it may not. Whatever the compiler is doing, is trying to do, can already be done by the hardware without incurring the code bloat that is possibly associated with super block scheduling. So it may not super block scheduling may not be so effective in superscalar process
Okay.
with out of order execution capabilities.
yeah, our all the experiments were in the in order embedded devices, like of course Qualcomm chipsets.
Okay. Okay. Great.
Yeah.
Great. Great.
So
Thanks.
so this is why it's more relevant to this.
Mhm.
So okay, I won't go into the details of the trace selection algorithm, because it's a very simple algorithm, work list based algorithm. So essentially we just so what we do is, um, we start with a node with a very high execution frequency, and then try to build the trace forward. That is, pick pick the successor with the most highest probability of highest probability edge, and then add to the work list, and then again we take the next we go on like this. Similarly, we try to build the trace backward. So this is, in the interest of time, I'm not going into the details of this, but this is a very straightforward algorithm. Only thing is, we have to define thresholds, like what is the, some thresholds, like we don't want to um, we don't want to uh, continue building traces if the probabilities are not sufficiently high. So you can go through this. So so there are some concerns in embedded applications, like
So
what
just one second. So we can share the slides with you, Suresh, and then you can share it with the students, because this is
Sure. Sure.
approved for external sharing. So
Yeah.
we'll
Definitely.
be
Thank
able
you.
to share. Also on the Halide, we have an extensive online training, the 4 hours in detail. If somebody wants to program the image processing stuff in Halide, we will send that link also to you.
Sure, definitely. That would be great. Yeah,
Yeah.
sure. Thank you, Sushi.
So, so we saw that super trace scheduling involves code duplication, and even superblock scheduling involves code duplication because of tail duplication, and also because of when we move instruction below a side exit, then we have to duplicate code. But this is a strict no-no in embedded applications where often code size is very important. So we can't afford increase in code due to tail duplication or fix-up code insertion. So, and another thing is that embedded processes may not have support for speculative execution. So we already, we already saw that we cannot move any instruction that may result in an exception. So this means that we cannot move loads or stores or floating point instructions which may raise an exception freely. So how do we address this? So what we have done is we have terminated traces immediately before side entries. That means that the traces themselves will not have side entries, and they are like super blocks only. So we don't need any tail duplication. And also because we are like because they are by default super blocks, we don't need any fix-up code insertion. That is characterized in trace scheduling. Secondly, we will not allow downward code motion across side exits. That means that we don't have to duplicate code across side exits. And thirdly, we are not allowing loads or stores to be moved um, away from their original basic blocks, so that um, so that our concerns of uh, exceptions are not there. So in order to relax these constraints, we have to show that they won't generate exception when the side exit is taken. Okay, so we implement we have an implementation of this in LLVM with all these restrictions. So where we replace the machine scheduler pass with our superblock scheduler pass. So what we, in the superblock scheduler, first we construct traces, then uh, we don't really have to do any transformation because our traces are already super blocks, so we don't have to do any tail duplication. So for each super block, we just construct the data dependency graph and schedule. So okay, so these are some of the implementation details. So maybe we can skip the first part, like how this design of this superblock scheduler graph class. So it that is an LVM specific detail. But how do we enforce these constraints? We have some restrictions, like, right? So for consider the
Arun, I
yes.
have one quick question here.
Yes, sir.
So do we do this superblock scheduling on the LLVM IR or after the code generation?
Yes, sir. We do it after in the machine IR.
In the
Like
machine IR. Okay.
yeah, yes, sir. Not LLVM IR, but
Okay.
in the after code generation. That is the we are at machine IR level.
Okay. Okay. Thank you.
So it's just a replacement for LLVM's machine scheduler. So it's at the same level as LLVM's machine scheduler. Instead of running machine scheduler, LLVM's machine scheduler, we are running our superblock scheduler. Okay. So the edges are exactly specified by these second points, like DDG edges for superblock scheduling. These are exactly the edges that we add. So the black ones, the uh, edges that are described in black are already present in LLVM, the already added by LLVM for by schedule DAG inst class. So the ones in red are the new edges that we add. For instance, we add an edge from an instruction to its terminator branch. This is in order to ensure that an instruction is scheduled before its before the branch that terminates its basic block, so that we don't move an instruction below a basic block, and we avoid the code duplication across side exits. Okay. Okay, so we also add an edge from a branch to instruction if in order to, if that instruction defines a register that is live in at one of the terminators of trace successors. So this is in order to prevent movement of instructions above a side exit when the instruction defines a value that is live in at the terminator's side exit. Similarly, we have in order to ensure that loads and stores are not moved across branches, then we insert edges from branches to a load or store. So from a load or store to another branch, that is already taken care of by this edge. So another edge is like if we have a call instruction, then we have to add register based dependencies among the registers that are modified by the call. So yeah, and yeah, so this last one is a implementation specific thing, so we can, I mean, we can ignore it for this purpose. So yeah, so even though this superblock scheduler has a lot of restrictions, it gave us some modest performance improvement. Like for instance, in one benchmark, we could get up to 6.15% improvement. In some benchmarks, we didn't get benefits, but in an important benchmark, we got some benefit, which was good. Because even though it was very simple, and it gave us this result. So computation was sometimes moved across two basic blocks to hide latency. So these are some of the limitations, and which we are planning to address in our future work. So this scheduler doesn't preserve debug info and doesn't model register pressure, and it's overly restrictive because moving loads across above their original basic blocks may fetch more benefits. So in order to do that, we have to show that the loads won't generate any exception. So some kinds of loads will not generate exceptions. For instance, if we are loading from a global symbol, then we are sure that that address is valid, and therefore it's okay to load. Similarly, if we are loading from a stack, stack based address, provided that the offset is within the bounds, then we are sure that that load will not raise an exception. So it's okay to move such loads. Secondly, downward code motion may be allowed if the result is dead on all off trace paths. So that this is if we we can relax, we make these relaxations without adding any overhead code. And thirdly, the scheduling decisions are based on single issue processor model. So it's very straightforward to extend it to multi-issue processors, because we can leverage on LLVM's hazard recognizer class that will be implemented by sub-targets, by their targets. And another very important thing is that better alias analysis may allow reordering of loads and stores. So this is a very, very important thing. So if we have very good alias analysis, then we will be able to move loads above stores, and therefore we can hide latencies better. So these are the references to the original papers. So we have so we just made some, I mean, the changes that we described in the slides in order to make it relevant to embedded processors. So thank you very much for your time. Is there any specific question that you have?
First of all, thank you, Arun. It's really good talk. Especially many ideas that you presented in today's talk, I didn't discuss earlier in the class. So it's a good thing that students got an opportunity to get exposed to these ideas. So one question is, in your experiments, did you try to give a free hand without worrying about code bloat? If you just go ahead and do aggressive superblock scheduling, what is the performance you get?
Sir, actually, we didn't do that because because it will be interesting from a I mean from a practical perspective. It is not interesting for us. So we didn't really, because our customers, I mean, for us, code size is very important. So we didn't do those experiments.
I mean, let's say, even if you do it, what is the percentage increase in the code size? Do we have some kind of idea on it?
So sorry, sir, I don't have that data,
Oh,
because we didn't perform that experiment at all. So
that would be, I thought, just to to get some kind of idea on where we stand. So if you're a bit aggressive, then if you relax this constraint, is the code size going to bloat by 10%, 1%, or if the code size bloat is 1%, but the performance gain is 10%, then maybe we may want to consider depending upon a use case.
yeah, yes, sir, that's a very good feedback. We will try that. Maybe we'll do some experiments on that. Thank you very much, sir.
Thank you, Arun. So I want students to see if they have any questions. So any questions, please, you can unmute yourselves and ask. So it's,
Sure. Yeah, please, one thing just I wanted to add here, please go ahead and ask questions. And believe me, with the hardware getting more and more limited because of narrow channels getting through the low nanometer technologies, leakage currents rising too much because of heating in embedded devices, especially the handheld devices. Because of the heat generation, most of the time you are throttling the MIPS. So our compiler optimizations are playing such a big role. You won't believe that. Like, we give a second life to a chipset before the next hardware is taped out just by compiler optimization every year.
very good to hear that, actually.
So in
I thought we
embedded,
just teach all these algorithms in class, but
without a good tool chain, let me tell you, like, for example, the AOSP tool chain comes with all Android releases, but Qualcomm does their own proprietary. The reason being, our tool chain, which we have modified, because in LLVM we can keep 3% code as private. So our tool chain on the same Android release among our top silicon competitors, some of the scenarios are working as much as like 80% better, because we did that optimization in the tool chain. Because Android is same for them, for us, it is same. Just it was because of the tool chain. There are some magic we did in the 2 generation back camera, where some of the changes in tool chain had those preview scenarios working 87% better, a particular use case. So there are enough magic in embedded world. There are enough magic being done in the compiler tool chain to, because this is a open, like, you can download our tool chain from Qualcomm DevNet. You can download the ASP tool chain, and you can try itself on your Android. So like how much difference the tool chain can make. So compiler in case of embedded devices is making, sorry, LLVM and tool chain optimizations are making huge difference uh, in embedded devices. Huge difference.
Nice. Actually, yes. So most of the time, our eyes are always on the Intel processors, but they are different beasts altogether, and we miss very
So
important space.
so there what happens is with the being power connectivity available, their optimization or them for toolchain optimization may or may not be
Yeah.
so important because cooling is also pretty much better than the handheld devices. And the way handheld and IoT devices are blowing up, not only this, sir, like just for the students, I will share because you must be definitely seeing in the papers. Like there are IoT devices which will get deployed in such a remote area that somebody will come to change their battery in once in 10 years. Now you have to you have to save every milliampere, every microampere for battery to run 10 years. Means you have to do more in every MIPS. So where all these things will come up from? Because earlier, like in case of Intel x86 or the bigger processors or the server side, okay, we have a 220-volt power cable there. You don't do, whether you do in two MIPS or you take a couple of more cycles, it's not a problem for us. But for embedded IoT devices with this 5G making it with the low latency internet coming in with 1 Gbps everywhere, the amount of embedded devices and sensors will get deployed on the network where we will have to do at very small current, very small using small number of cycles. So tool chain is going to play a very big role. So that's like our view. Qualcomm invests so much in tool chain uh, uh, for obvious reasons.
And just to add one more data point actually to emphasize the importance of the tool chain, like it's not just for academic purposes. One of the problems, not just with Qualcomm, with all the other companies, is like there is a lot of legacy code that's there in all the applications. Like generally the new code, the code that gets changed is only 25%. So 75% of the code doesn't get changed in most of the cases. The reason is for that is like no one wants to go back and change the old code because no one wants to take the risk. Something is working, they don't want to optimize it and with a potential risk of breaking it. So the only way that we can extract better performance of the old code is by the compiler. Like compiler optimizations can probably generate a better code for the legacy source code and can improve the performance. I mean, that's the only way that the companies, uh, that's the only approach that the companies would like to take. They don't want to go back and change the legacy code. So it's very important for the tool team, for teams, or for the compiler teams to make sure that um, uh, even the legacy code works well efficiently on the new targets, on the new hardware.
One last point I will add on the toolchain importance. This is not a toolchain marketing session, but still the last point, like I forgot the name. Someone machine learning top scientist recently said this is the era of dumb programmers and smart system engineers recently. For example, that with the TVM and the AI graph compilers. So now on Qualcomm chip, people will write, like earlier they were writing in C or assembly, the optimized NN codes or machine learning. Now they will write a Python code for machine learning, and our toolchain engineers will optimize it for Qualcomm hexagon chipset. So dumb will make, like dumb programmer look smarter using toolchain, because in Python you cannot optimize it for particular target or anything like C or C intrinsics or assembly. So toolchain is going to be, because so many architectures, you cannot have so many people to understand so many architectures. Also there is a problem of portability. Like for Halide, people code in Halide, people write their own optimized compiler so that Halide runs well on Qualcomm Hexagon, Halide runs well on Samsung Exynos, on Siva, or any way they want to do it. Similarly, it is going to happen with machine learning. People will write the same models in Python, and people will write a great tool chain, so it works great on Hexagon or all other DSPs or CPUs, because portability is extremely important. Engineer productivity is extremely important. So a big example is TVM, Glow, all these things which are coming in. And just
Thanks.
not to leave introducing Arun. Arun is one of our most humble persons in our team, and he even like a fresh engineers, he addresses them with so much of respect. And Arun is the masters from IIT Madras and PhD from ISC Bangalore under Dr. Vayan Shrikant, and one of our like most respected team members and most humble team members in the team. And you can reach out to him anytime. You can send him message. He will always respond to you if any of the students want to reach out to him. Thank you.
Yeah, thanks a lot, Sushim and Ravi and Arun. So I can see from Arun's talk that he's excellent talk, but he's so humble. I completely feel what you're saying. It's great. Today's talk is great, and all the insights that you have provided, they give new perspective to students, to me, faculty, also inputs on driving our research, what problems to consider going forward. So it's all very valuable input. I really would like to see that we continue this engagement going further in some form to like just some some talks like this on and off really helps in the exchange of ideas. And
Sure, sir. We are also preparing for it because it's mutual benefit for both academia and industry, as I say. Because the way you said, like you understand the industry problems, and for us, what happens is for Qualcomm, there is a big pursuit that a lot of things which world still thinks that it is academic and not commercial worthy. We always try it. Like polyhedral, we commercialized uh, at least 5 to 6 years ahead of the whole of the industry. So for us, that is the benefit we hear from the industry. We generally get some of the PhD candidates to intern with us, and we hear what is going on academia. So it's a mutually helpful relationship, sir.
nice. Very nice.
Yeah.
So I think shall we conclude today's session, sir,
Sure,
if it's
sure,
all
sure.
good?
Sir, no need to call me sir. You have official right to be called sir, being the teacher. But we don't have any right to be called as sir.
No, not at all like that. Yeah.
Yeah.
So we'll, so yeah, as I said, so we'll conclude today. Thank you again, and we will
Sure, sir.
be in touch. And
Yeah, we are working on getting our TVM talk in the open, like legally approved by Qualcomm, because
okay.
TVM will be more of interest, because nowadays anything you add machine learning in front of it, whole world gets interested. So since TVM is making like it's a ML AI graph compiler, so maybe more people will be interested. In the next session, we can do the TVM introduction.
Sure, definitely. Yeah,
Sure.
definitely. Great. Thank you to all the students, and have a great day,
Yeah.
everyone.
Sure.
And
Thank you, sir. Bye.
okay, bye.
Thanks, sir. Bye.
Thank you all. Bye bye.